eventually make it. So what I want to talk about today is some novel effect associated with boundary field theory. And the way I'm going to arrive at this result will be using anomalies and also using holography. So holography is something which string theory community has developed since the last 20 years. So in particular, I would generalize this holographic duality to the system with boundary. So for boundary homological field theory. So these are my collaborators, and the work is based on a number of papers which has appeared on the web since last year, and including I will talk about some work which is in progress, which should appear hopefully this week. So this is the whole of my talk. I will first start with some motivation, and then I will talk about this real universal effect in boundary homological field theory, which exists in the form of the induced current. I will explain how this can be obtained from field theory by relating the effect with anomaly, which is another well-known universal effect in field theory. And then I will explain the boundary holography and derive the same current, the same result using holography. And I explain how this idea can be generalized to 6 dimensions. In 6 dimensions, of course, we live in 4 dimensions, but if you work in string theory, then we believe that the world actually there's a more fundamental formulation which can resolve some of the problems we have heard so far, like hierarchy or etc. etc. It's based on the theory of strings, which has a strongly coupled limit in terms of 11-dimensional field, 11-dimensional theory called M theory. And there's a very interesting system which is 6 dimensions. And that system has a lot of things which we don't understand. This is the typical thing we have in string theory. There's a lot of things we don't understand. So I will use this idea to learn something about this system. In particular, we can learn about the form of the wire anomaly in this 6-dimensional M-dimensional system. And then I summarize. So motivation. The simplest boundary effect, which is also one of the most important effects we know about in quantum field theory, is a Casimir effect. It's this tiny force between conductor. It's basically it's a measure of the energy of the ground state of a vacuum in response to change in boundary conditions. So the Casimir effect is a force. It's an energetic response of the vacuum to change in boundary conditions. So the motivation for me and for our work is that is there any other non-trivial lawful effect associated with boundary homological field theory? Let's say boundary QED, or QED with boundary. So in this talk, I will explain there's the refined one, which is quite simple in this figure here. So there's a conductor, let's say this is a conductor, and this is vacuum here. And then we turn on the B field in this direction, going to the board. And we find that there's a current parallel to the boundary created, and it obeys this form. C is the constant, and N is the normal of the boundary. So at this form. So one of the goals of my talk today is to explain this result. This can be, as I said, this can be derived both from an exact analysis of boundary homological field theory using a relation which we can establish between the current and anomaly. And also it can be established using ADS BCFT. So in the session 3, I will then extend the idea. So this induced current, as I said, it can be derived using both ADS BCFT and also a relation with wire anomaly. In 6 dimensions, we know very little about the wire anomaly, but the method using ADS BCFT can still be applied. So in that case, we will use that to derive properties of wire anomaly. So basically, that's the logic and the flow of my talk today. So let me, as a warm-up, let me go back to the Casimir, well-known Casimir effect. Of course, Casimir effect is well-known. You can compute it using just a textbook quantum field theory. But suppose you want to do a more general setup, a arbitrary shape of boundary, and you want to know about the stress of the vacuum acting on due to vacuum fluctuation on the boundary. So that means we have to study the one-point function of the stress tensor in the presence of a boundary. So that in the presence of boundary, that is not 0 anymore. So it can have a asymptotic expansion like this in general. H is the distance of the boundary. And it is just something which you can do by imposing dimensional analysis and also energy momentum conservation. And these are the consistent solution, the form of solution you can have. So H is the boundary metric, K is the exterior curvature of the boundary surface. So basically it's the derivative of the metric, the normal derivative of the metric, and then you have basically it's a derivative expansion you can have here. So without going into the details, so basically the structure is that you have some geometrical this like curvature or covariant derivative, geometric structure multiplied by some constant, dimensionless constant. Those constants are the physical constant which depend on the theory. So imagine you use suppose you consider 3D, and you set one set of constant. If you do a free fermion or etc., then you get another set of constant. So people before have done this computation, but obviously only for very simple setup and very simple field theory one can do this. So so the whole structure of the stress tensor is basically determined by this Casimir coefficient. What we find in our work is that this Casimir coefficient actually completely determined by the boundary central charge of the system. So the relation itself is universal. Relation between boundary central charge and the Casimir coefficient is universal. The boundary central charge itself still depends on the system, but the relation is universal. Now, just let me go back and just explain what is a wild anomaly. In general, suppose you have this W is the effective action of your theory. It will depend on a lot of things, but in particular, let me single out the dependence on the metric in which your theory is defined. Then you can scale the global rescaling of the metric. This is called wild rescaling. Quantum mechanically, this is not necessarily equal to 0. For a conformal theory, it's equal to 0 classically, but quantum mechanical effect will leave a non-zero, and then this is called the wild anomaly. So it's an anomaly for global scaling. In general, this wild anomaly can be measured by the trace of the energy momentum tensor. And in general, it has two contributions. One is the integral over the bulk, over the whole manifold. In the place of a boundary, you also have the boundary contribution. This is called the boundary anomaly. So all this has been studied for many years. So for example, if you consider multi-field background of metric, then all these are well understood. All of them has been classified by Tesla, Streamer, and also recently by other people. For example, three dimension, let me just say, in three dimension we know there's no bulk wild anomaly or dimension, only a boundary one. The boundary you have this term. So we have two boundary central charge here, B1, B2. In general, the boundary central charge will depend on boundary condition. Yeah. Yes. So I put it as a theorem because I did this talk actually last week in Singapore. It's a math physics audience mixed. So to please the mathematician, I put theorem. So anyway, there's a relation which you can easily establish just using the properties of the effective action and how the effective action scale will change when you change anomaly, change the scaling, and there's a relation between the variation of the anomaly with respect to an arbitrary variation of a metric. So you know the anomaly, you take it from the literature, and you change the metric, and in principle you can compute this quantity, and you look at the boundary component, boundary component of this wild anomaly variation. And what we find is that it's actually related to the stress tensor, this integral here. You regulate the manifold with a UV regulator epsilon, and you extract the logarithmic term from this thing, and you get this. It's very easy to establish. But this is quite powerful, this relation, because the right-hand side, the left-hand side, this is a total variation. This one is not a total variation. So in principle, this is like an integral condition. If we impose a lot of condition, for example, on the structure of T. So basically, using this, we can fix the form of the Casimir expansion of the energy momentum tensor or boundary CFT. So this is what we did in this paper here. Universal, just as I said, the coefficient will be determined in terms of the boundary central charge in a universal way. Although specifically for each theory, you still have to compute the boundary central charge. and they differ theory by theory. But the relation themselves is universal. So let me give an example. For three-dimension, we know that for three-dimensional CFT, there's only boundary anomaly. So this is the form. You have the R term. This is a rigid scalar curvature for the boundary metric, and this is a exterior curvature, K squared. And we do variation. So this term doesn't have any variation because this is actually a topological term. This is like Euler number, right? So only this term. So you get this, and you substitute. Now we substitute T mu, the Casimir extension we have, into the integral we want to compute, and we get this. You get the logarithmic divergent term like this. So we compare the two expressions. The first, this one has a B2, so this can be compared with this. So B2 has to be equal to minus alpha 1, and then all this has to be 0. So the Greek letters are the Casimir coefficient. They are completely determined in terms of boundary central term. So this is the way it works. And similarly, we can do it for 4 dimensions. So now we are ready to do the to introduce the effect which I announced in the beginning. So for a little bit more background, so we're interested in the current we are talking about can be embedded in the larger background of work in the community of so-called anomaly-induced transfer of charges. So what is known in the literature since early 80s is that because of the chiral anomaly, the standard anomaly for the chiral axial transformation of fermion, there exists a induction of current if one turn on the B field. So for example, in this chiromatic effect, you turn on the B field, there's a current induced in the direction of the B field with the coefficient which depends on the chemical potential. This is the axial combination and the vector combination of the chemical potential. So this effect exists when only if you have a finite density of charges in the system. And so not for vector. Yeah. So you also have another effect which is called the chiral-rotational effect, which is the effect that if you rotate like a plasma, for example, if the plasma itself has a chiral anomaly, and there will also be a current. So if you drink Coca-Cola in this system, be careful not to stir, because then there will be some currents going to your mouth. They kill you. Yeah. It's not a good joke. Okay, so again, the coefficient depends on the chemical potential. And there's also a t-square dependence here. This comes from the gravitational anomaly. Anyway, so this effect were one of the motivations for my work. When I learned about this, I asked myself, we asked ourselves whether there exists similar effect, but not without the presence of charges, without chemical potential. Can we have such an effect just for vacuum? Yeah, this is the motivation. So we thought, so combine the Casimir effect, we know there's something interesting for Casimir effect because we can do it for vacuum. So we want to know whether there exists some anomalous transport effect for vacuum. So this is the question. If possible, how? So now I show you how. So basically the question was asked later. I mean, in the beginning, we just followed the Casimir work, and then the actual extension for the work is to consider instead of two form, because the conserved current. So we do the same analysis as the energy moment tensor. So we say, okay, let's say we have a conserved current, and then what's the form of the conserved current in the presence of boundary? Then we do the same exercise. So we write down the extension, and then solving the conservation law consistent with the gauge symmetry in the system. And these are the possible form of a solution. These are the coefficient, like the Casimir coefficient. We call this a current coefficient. And similarly, now suppose you have an anomaly. The anomaly will depend on both the background metric and also the external background gauge field. Now suppose you change the background gauge field, and there's such a relation, which is you can establish similarly. Once you have this, and also we know the anomaly, the wild anomaly. So this is not the chiral anomaly, the wild anomaly now. Wild anomaly, since the 80s, Collins and Chong analysts and other people, they have computed in particle physics, certainly well-known result, that there's such a wild anomaly contribution from the background gauge field, and B1 is the beta function. So if you substitute this result here, then you just work it out, and then you find that J has to have coefficient like this. So if J has to satisfy this form. This is the result I found I announced in the beginning. So we have such a current. Now the current itself is now completely universal. The only information about the system is in terms of B1, in terms of beta function of the theory. And it may sound strange where the current comes from, right? It may not be strange, but I want to make it more strange, so I say to you it's strange. Now I want to explain why this is actually completely natural, reasonable. There's a very easy understanding of this effect. So here, I consider a point above the boundary, there's O here. There are vacuum fluctuations which create a positron and electron vacuum pair all the time. So this vacuum pair, after they are created, they will follow a circle because of the B field. And when they hit the boundary, they cannot combine. If this point is very far away, then they can complete the circle. So in the end, nothing really changed. They are close to if this point is close to the boundary, then there's a separation of charge because the charge cannot be combined. Suppose this is let's say perfect conductor boundary condition, it will be reflected. So there will be a separation of charge. This separation of charge, invisible, you can try to calculate from quantum field theory, but we did it with anomaly, and that's the exact computation. So that's the one reason why we have the current. Another equivalent way to understand the current is by looking at, let's say, each of the particle itself. So that this particle, so let's say this is the B field. The particle, the positive charge particle will move in a circle like this, clockwise, and the other one will be anti-clockwise. No matter what happened, this is correspond to some tiny current loop which create dipole moment, magnetic dipole moment. These two actually add up. So what happened? So what I'm saying is that in a vacuum without boundary, this is happening already. If you turn on a B field, you always have this infinite amount of magnetization in the background. But then it's just a constant, so we normalize that way. There's no physical effect. But in the presence of boundary, the loop which are close to the boundary will be stopped, and then they will cut. The loop which are far away, they still form a loop. So in the end, you create a non-uniform magnetization density in the vacuum. So we normalize magnetization density is non-uniform after you do the subtraction, because the one close to the boundary, they are stopped, and only partial current form. So in the end, we get a magnetization current. So the same as the one we get from anomaly. So this is the interpretation of the current. This happened. It's a well-known effect in plasma community. They have a magnetization and magnetization current. So this is a similar one, except this is for vacuum. So invisible, this can be observed. So we are talking to some experimentalists who did observation for isolated effect to see how this is can be done. So now we want to understand the same effect using ADS and BCFT. So in the standard ADS CFT, we have a boundary theory M, and the dual is given by ADS state. Now, if the theory now has a boundary like this one, M here, with a boundary, where boundary is like a circle here with a P, and it was proposed by Tanakayaki 2011 that the dual is given by a portion of the ADS space. So if M is infinitely extend the whole R4, then it's whole ADS. But if it's only a portion of the R4, then it's a portion of ADS space. So the whole procedure depends on what is the shape of this cube here. So once you know the defining manifold, and the rest is standard, more or less standard. For people who do ADS CFT, we start with the Hilbert-Einstein gravity action with some given Hawking's boundary term. Except now we also have a Q boundary, right? So because our Buck manifold has both the M boundary and the Q boundary, and also there's a this junction, so-called junction for the GR community, is a place where the normal of Q and the normal of M are not continuous. So this is some kind of a discontinuity. So in order to have a well-defined variational principle for this system, we need to have the boundary term, different Hawkins boundary term for Q also, and also this junction term, which is beta is basically the discontinuity, the angle of the normal when you cross P. And in principle, one can also add this term here. It's a constant. So this is what Tanagaki proposed to do. And what he finds is that the T is a measure of the boundary degree of freedom, given on the boundary of the boundary CFT. So if your boundary, the boundary can be analytical. You can also put something there. So T measures the boundary degree of freedom. Okay, I think we're going to skip this. Now let me just, because of time, let me just say at the end, the equation which determines the Q is given by this equation. K is the scalar exterior curvature. So the surface is a curved one, so there's exterior curvature tensor, and you take the scalar contraction of that. It's equal to D is dimension of your field theory, and T is this parameter I put in the property description. So if K is 0, this is like a minimum surface. Otherwise, this is just a constant curvature surface, which is something mathematically may be interesting also. I think here is definition like this kind of thing also. Okay. The slide I skip is basically commenting about why this proposal, we should believe in this proposal rather than the one Tadashi proposed, because Tadashi proposed basically something which is a tensor set of equations with many components, and here is only one equation. And this should be the case because actually the embedding of Q is defined by just one codimensional embedding, so there should only be one equation rather than many equations. Okay, but these are you are not working in this field, so I think it's okay. How much time do I have? You don't need it. Okay. So for people who it's a bit technical here again. But for standard ADS-CFT, because there's no such a junction there, so what we always do is doing something called the FG expansion, Fairman-Graham expansion. It's an expansion for writing down an asymptotically ADS metric. So we are interested in not exactly homology theory in general, but some some boundary field theory which are in the IR limit is in the UV and IR limit is conformal in UV limit in particular. So in general we are interested in symptotic ADS metric. So if it's an ADS metric, dg is just a constant like delta ij. But if it's symptotic ADS and in principle, then you have the expansion, some C dependent. Right. So the idea is that this metric still have to satisfy the Einstein equation. So usually people can you just assume this expansion and then you substitute back and you can determine the next order term of Einstein equation. And then you can do a lot already with ADS-CFT by assuming this expansion. This expansion was developed by these people, mathematical community. So in history originally. In our case, of course, this expansion doesn't work because, as I said, there's a discontinuity here. So what can we do? Either we solve Einstein equation exactly, which is quite hard, or we find another expansion which allows us to do something. So what we find is that we can identify another expansion parameter. So let's go back to the field theory. In the field theory, basically you should imagine you have a boundary like a circle, and then the natural choice of coordinate in that case is something called a Gauss normal coordinate. So X is the location of the boundary. If you stay at the boundary, then you get this sigma is the boundary metric. So just fine, just a boundary, just a metric. If you go interior, then you try to feel the curvature of the boundary, and this K describes the curvature, exterior curvature. So this expansion is called a Gauss normal expansion, Gauss normal coordinate. So there exists such a coordinate around the boundary point, and then you can write down such a nice simple expansion of the metric. Using this metric, now we can see that if we assume the k is small, so we can use that k as an expansion parameter. So using that, then we can solve Einstein equation. So in construct a quadratic solution in terms of expansion of k. But in this case, the C dependence is now exact. So we don't suffer from the discontinuity problem because this is now under control. So now we can then use that to study the current. So to study the current, the boundary current is coupled to the boundary gauge field. In the ADS-CFT, this boundary gauge field comes from is the boundary value of the Buck gauge field. So the Buck you should value to the Maxwell Lagrangian. So this F is a dA of a 5-dimensional gauge field whose boundary value is a 4-dimensional Maxwell field. And we just solve the equation of motion for this F in this asymptotic ADS background. And this is what we find. And then we do the variation, compute the current, and then we find this. So this is in this thing without any unit. So if I put that to Newton constant and thing, then it can be put back in the form with the correct unit. So this is basically the way we can get the induced current from ADS BCFT. Now I go to 6th dimension. So in 6th dimension, as I said, okay, there's a motivation to go to 6th dimension because in 6th dimension we have something M, so-called M fibrate in M field, and that's a very important and interesting object. And we don't know much about this theory, so this is this is one approach to learn something about that system. So current in 4 dimensions, or a particle, in case of a particle would trace out a well line, and the well line gives you a current, right? This is a current, and the current coupled to a background gauge field, and so it gives you the minimal coupling. So this is a simple exercise. Now we can generalize this to high dimension. Let's say now you consider a string, and the string has a well sheet. So x mu is the just a well line. Now we have a well sheet. The well sheet depends on sigma coordinate, sigma 1, sigma 2. So this is the string current. The string current again coupled to the B field to give you the minimal coupling of the string well sheet to the B field. So this is very simple. I just do this because we recognize this coupling is very important because this is a coupling which allow us to relate current with a Y anomaly before. So now with this coupling for string, I want to so we can forget about this. This is what we know about trace the Y anomaly in 6th dimension. But we don't know anything about, like, suppose you turn on a 6th dimension, you have a two-form tensor gauge field with a 3-form field string. We don't know how that field string will contribute to this, the Y anomaly. So we now want to use this to see what happens. So this is something which we can establish similarly to the 4-dimensional case. Now, why I'm saying is that in 6th dimension, we don't know the similar expression like colons and joiners for the trace and for the Y anomaly in the background of a 3-form field string. That is unknown. But we know about this because this current, I will show you in a second, we can again use the ADS BCFT to derive this string current. So in the presence of a 3-form field string, again, string will start to move around the boundary. So this is similar. So then we can use this and try to solve for A, which is give you this result. That's the way we can learn about something. So the idea is similar. 6 dimensions, the deal is set in 7 dimensions. So it's a Hilbert-Einstein gravity with Cosmology constant, and then there's like a Maxwell Lagrangian for the H field. And one can derive this very simple. Similar form also, the current. There's a string current. So using that string current, you can substitute back to this relation and ask what is the consistent, how do you get this satisfied? So, and this is a solution. All this seems very natural, but nobody thought about this before. And also, it's impossible to derive it, at least now. I mean, we don't have any understanding of, for example, in 4 dimensions, you know the F square normally comes from loop. For example, you have external gauge field, EM field, and then you have a Fermion loop, and this gives you somehow anomaly. In 6 dimensions, we don't have this picture. We don't know how B mu coupled to method, for example. You don't have the coherent derivative. for quantum field. But you can write down something. I mean, you can write down, if you consider string, I mean, you are considered string anyway. So you consider string functional. It's like doing string field theory now. So C is a loop with the string, and then suppose you consider string functional. This is direct analogy of the quantum field, right? And instead of a usual derivative in which you change your position of the particle, now I do it where in general what I can do is that I change the shape of the loop. So the change of the loop will be covered by, we induce a change in the area. It's a delta sigma mu. So I can define this derivative. As long as this is well defined, I mean, not everything is well defined in calculus. Something is not well defined sometimes. But if this is well defined, then if this limit is well defined, then I can define a covariant derivative. It's a loop derivative, not covariant derivative. Loop derivative. So it's anti-symmetric in mu. Now, to introduce covariant derivative, and we consider gauge transformation. So let's say we consider a gauge transformation of the string functional like this. In general, it will be like this. I mean, in general, it will be a functional on C, but as a pairing, cost pairing, so you can always define one form so that you can write in the integral form like this. So let's say this is a symmetry or the theory. And you can easily check this is a covariant derivative. This is a Eulerian under a change, not Eulerian, covariant, under a change of the phase. If B mu here is satisfied, it's such a tensor gauge transformation. I have an analogy like Yang used. Yeah. So I don't have the complete theory, but I think this will be important ingredient to try to understand how the field theory of string can give rise to the anomaly, which I wrote down before. Right. We should not look at quantum field theory, but look at some string field theory and the functional. Okay. So that is for generic six-dimensional theory. But for M fibrine, because of supersymmetry, M fibrine has so-called 2,0 supersymmetry in 6 dimensions, and the multiplet of the 2,0 supersymmetry is constrained, and the field strength there has to be self-field, so it's more restricted. So at the story stop, the solution I had before for the anomaly was assuming the B were independent. But if you have self-duality, the B cannot be all independent. So in that case, you have to try to solve the equation again. So we solve it again, and we find a different solution. Yeah. So this cannot be obtained from the previous one by reduction or restriction. It's just completely different. Okay. Now, what I said before, I have determined the current form of the current up to coefficient. Now let me put back the coefficient. So in the ADS 7 duo, we know the Newton constant, we know the radius of the sphere, all this. So we can put it back. And the important thing is that the solution was as n dependent, which depends on the number of n of the M5 ring. And if you put it back, then we find this interesting factor of n cubed. Now, okay. Why is that interesting? In 4 dimensions, we will find n squared, because this n squared or n cubed there basically denotes the number of freedom moving in the loop, which contributes to the current. And this n cubed appear suggests that actually there are n cubed variety of degree of freedom in the theory, which contribute to the current. And this is a puzzle. Why is that interesting? Because it has been a puzzle. How to write down the n multiple n number of M5 ring theory. We don't know what kind of base group and what kind of mathematical structure is part of it. And n cube suggests is consistent with some other consideration. Yeah, people. I don't have time to tell you, but it's kind of nice to see it again. So conclusion. We found new universal relation for boundary behavior of stress tensor for Casimir effect and current. In the presence of a magnetic field, we predict a magnetization current in the vicinity of a boundary of a QED vacuum. So I try to make it very simple to understand in terms of magnetization. So this effect is like the response of a vacuum to magnetic field. So I call this a magnetic Casimir effect, and that's the reason in the title I have. You see, magnetic Casimir effect. Based on the original work of Tanayaki, we have constructed a complete proposal of holographic BCFT, and we also predict a form of the wire anomaly for M5 system. These are some open questions. We don't know the origin of the wire anomaly. It would be nice to work it out. So, what's the integration of the partition function? Can we get some constraint, for example, on the partition function? Quantum Hall effect, actually our effect is very similar to quantum Hall effect. Quantum Hall effect can be understood in terms of non-computer domain. I mean, this condensation of the center, guiding center of the Hall effect. So, the guiding and quantum Hall effect, this geometry play an important role. Now, can we understand our magnetization current in terms of non-computer geometry? That would be very nice if I can understand this, because, and that means, and I probably can also understand the string current, induced string current in 6 dimensions from some type of non-computer geometry. This kind of non-computer geometry is not known. We don't have any idea what kind of a bracket, for example, this could be. So this kind of analysis has the potential to tell us something about this also. Thank you.
Okay, so we can allow one short question.
So you interpret the current as a result of creation of electron-positron pairs in the magnetic field.
Yeah.
But how is that?
And it's not really creation. Yeah, but okay. It's a virtual creation.
Yeah, virtual creation. Yeah, but how is that conceptually related to the scaling of metric in our anomaly?
Oh, no. So it's a completely different effect. I mean, wire anomaly has 2 contributions. One is a metric contribution, like curvature, and the other one is a background gauge curvature contribution. So I'm talking about the later one. Yeah.
Okay, thank the speaker again. Next part by meeting 1.